against you, court of law. I mean, goes public. Hello and welcome back to differential equations. You're live. Yes, Chewbacca. 1.2 general and particular solutions. And this is where we understand the difference between a function and the function. So there is a difference between a and the. When you say, you know, a man or a woman approached me, it's like a general term. When you say the, it's a particular person. So now, when you have a solution to differential equation with plus c, it will be a general solution. And when you have constants, it will be particular solutions. We're going to go all the way back into pre-calculus 1, where you learn shifting functions up and down when you add a value. So in pre-calculus 1, you learn that if you have f of x as a parenting or a general function, right, default state, you will say that f of x plus minus c would be the same shape of the function shifted up c units or down c units, depending on plus or a minus. So now, on top of that, which is mainly graphically, thinking graphically, we're going to jump into calculus 1, and we're going to recall that the derivative of x squared is 2x, and also recall the derivative of, let's say, x squared plus 10 is 2x. This is what makes us say that the integral of 2x dx is x squared plus c. Derivatives destroy this information, the constant, right? Because no matter what number you put there, derivative of it will always be 0. So when you undo the operation, you don't get particular function back. You get the family of functions back, infinitely many. So in this case, when you are thinking about the function, you have particular functions like x squared, which goes through the origin, or x squared plus 10, that grows to 10. So these are the two functions that we have within the derivatives. On the right-hand side, we have x squared plus c. And x squared plus c is going to be the family. So I'm going to use these dashed lines and tell you that we are preserving the x squared shape, but we are going to have infinitely many of these stacked on top of each other. And we get to change this into a particular one if we are able to figure out this value for c in some way. Now, you do learn that all the way back in Calc 1, section 4.9, if you use the current textbook. And when you learn the antiderivatives, and you learn there that if you have an integral that you need to solve, and you have a point called initial condition, let's say, there are other ones, you can figure out the value for c. So if you are supposed to integrate, say, x squared minus 2 dx, and you are given that f of, I don't know, 2 is 6, whatever, we can solve the integral and then use that information, which also could be represented as 2, 6, use that information to calculate c. So now what I'm going to do is I'm going to integrate here, get x cubed over 3 minus 2x plus c, and now use the initial condition where I understand that everything will be equal to 6 and every x becomes 2. So I actually have 2 cubed over 3 minus 2 times 2 plus c equal to 6. 2 cubed is 8, so I have 8/3 minus 4 plus c equals 6. And it's clear that I can compute c from here, right? So that's going to be 8/3, so c is equal to 10 minus 8/3, 30, 24, 22, right? Something like that. So this one will be called general solution. And x cubed over 3 minus 2x plus 22 over 3 will be called the particular solution. And obviously, in order to have the particular solution, you have to be able to compute that c. So you have to have initial condition. If any one of you thought about making the turkey or a chicken using Newton's law of cooling, you know that you have to bake for some time and then check the temperature. That time when you check the temperature after, let's say, 30 minutes or 1 hour, that is you getting this so that you can finish off the model and do it. And by the way, it works like a charm. It's not just a textbook thing. All of the qualities of your oven will be buried within that K. We talked about Newton's law of cooling last time, which is also Newton's law of baking. And depending on just whether K is positive or negative, all of the qualities of the dish and the turkey and the oven, type of the oven and everything is going to be in that constant K. So the first time you take this temperature, you are actually figuring this out, and you can figure out the K. So within differential equation, that would be one of the conditions. So you're able to actually pinpoint the exact one that you have to use. We also did this for I didn't do it carefully. I just said let's call it, but now I'm going to go back to it. Remember last class we talked about acceleration, velocity, position? Let's just do one of them. So we said that acceleration was negative g. And then we said that dv dt, which is the acceleration, was equal to negative g. Then we separated variables. And then we integrated both sides. And then we got that the velocity was equal to negative gt plus some constant c. And at that point, I said, let's just call what we are learning now. Because at this point here, I'm going to say that velocity at 0 time is going to be called initial velocity. Now that makes a lot of sense, because at 0 time is where the system begins to evolve. So I have v of 0 equals v naught. And now when I plug that in here, that t equals 0 is going to wipe this term, and you get that v is v0. So you have your c, right? So the entire equation, so this is how it works. So now I'm just going to set here, I'll use red, say plug in. So your v becomes v0 minus g times 0 plus c, and you see that c is v0. Now I skipped this part last time. I just told you, c is v0. For population, I just said, yeah, p is p0. But you have this every time. At the beginning of time, there is something calculus-wise. At the beginning of time, which is at 0, there is something which will have to evolve and become something else. Because calculus and differential equations, it's a study of change. We're talking about derivatives, rates of change. So these systems have to evolve, have to change, and then they can be measured by calculus. Calculus cannot measure number 3. So there's no change there. What's the derivative of 3? 0, right? Calculus can't do anything about 3. You have concept of number 3, but there is no calculus regarding number 3. So this lecture is there for you to remember / realize the difference between general solutions and particular solutions. And every time when you have a constant given to you, you will be able to plug those things into the differential equation or the integral, depending what it is, to get this. Now, I kind of skipped a little step here, which I actually wanted to talk about, and that is the notion of how you solve equations. Remember, differential equation, right? So we know that we use inverse operations to solve equations. If it's x plus 3, we use subtraction. If it's 3x, we divide by 3, right? So if you have differential equation which contains derivatives, you should, common sense, integrate. Exactly. And with that integration, we are introducing an issue with plus c, which splits our answer into general solutions and particular solutions. Now, function part is the same. It's just that constant c, which shifts that shape up and down, which is what we learned in pre-calculus 1. So they gave us a few of these examples. They talk about, again, about acceleration and velocity. They talk about free fall. All of that stuff I did last time. I'm just going to pick on a few of these problems. The next section is done. We can talk about the next section. The class ends like 7 or something. What time?
4:50.
4:50? 7:50? 4:50. 4:50. So what do we have? We have 5 minutes left, and then another hour after that. Awesome. No, we have enough time. So let's solve some of these problems that you will really enjoy. I'm going to now, if I hit one of your homework problems, you just do all other problems. So that's fine. Because I want you to work on number 5. Now, if it's, and for homework, you do 4 and 6. dy dx is equal to 1 over the square root of x plus 2. And you have the condition that y of 2 is negative 1. So let's go. Separate variables, integrate the hell out of everything, use the initial condition, and get that particular solution. I didn't teach this yet. Class preps are before and homework is after. Oh, that's fine. That means you have less for next. See, you just freed up a time to watch a movie this weekend. It's amazing, right? Yeah. The rest, no movie. You have to do homework. Autocorrect. Word probably changed into propane. You don't even want to know the sentence. Worked out awesome. 44% of lights are out in this room. I was bored. All right, so you had sufficient time. This is one of the equations that you just move dx, because as you can see, all of the y's are already on the left, and you have x's on the right. You just need to move the dx. So we have dy equal to square root of 1 plus, and how do we integrate this? Okay, to 1/2, and then what? U sub, and then, yes. So U sub, and then you will do that, sure. So U equals x plus 2. Du is dx. We just plug everything in. So y equals, and you will have integral of u to the negative 1/2 du, which is u to the positive 1/2 with 2 in front, plus c. Now we go, I don't care about u, I care about dx, which means we bring x back, and plus c. At this point, we have the y of 2, right? We have the point, and we can say that 2 times square root of 2 plus 2 plus c is equal to negative 1. So that's 4 plus c equals to negative 1. C is equal to negative 5. So this one over here is what? General. And the one that I didn't write yet, so y of x is equal to 2 square root of x plus 2 minus 5 is particular. Green? All right, here is the next wonderful example for you to enjoy. Find velocity function and the position function given a of t is equal to 50 sine 5t with v0 being negative 10, and well, let's say x0, I can say s0 equals 8. Have fun. This is V. It looks like an alien letter. Let's take a look at this. So we are supposed to write change in velocity over change in time, that's the acceleration, equals 50 sine 5t. And we do the separation of variables, so dv is 50 sine 5t dt. We integrate both sides. One thing about integrating both sides, you do not have to put c on both sides, only on one. Because if you put plus c1 on the left, and plus c2 on the right, and then you go c2 minus c1, you can just call that capital C, right? So there is no need to put c on both sides. You put c only on one side. So now we have v is equal to 50, integral of sine is negative cosine 5t over 5 plus c. 50 and 5 cancel, and we get this general form, v of t is equal to negative 10 cosine 5t plus c. And we have a point 0, negative 10. So we plug in negative 10 is equal to negative 10 cosine of 0 plus c. Cosine of 0 is 1, negative 10, so c is 1. That's what I said, please pay attention. C is 0, very good. And we have the particular solution v of t to be negative 10 cosine 5t. And then you realize you have to do it one more time for position function. So change in s over change in time is negative 10 cosine 5t. Ds is negative 10 cosine 5t dt. Integrate both sides. Notice that I'm integrating, kicking the constant outside right off the bat. S of t is equal to negative 10. Integral of cosine is, very good, again divided by 5, plus c. These cancel, and we have this s of t to be negative 2 sine 5t plus c. Then we have s0 is equal to a number, 8. We plug that in, so 8 is equal to negative 2 times sine of 0. And how much sine of 0? Yeah. So c is awesome. So a particular solution for s of t would be negative 2 sine 5t plus 8. So those are the two functions they asked us to figure out. Happy? Of course, it's differential equations, right? All right. So let's take 2 minutes break, and I will restart the stream and get the new title and everything for the slope fields and solution curves 1.3. Bye.